Hello everyone, my name is Sakshi Rastogi. I am pursuing BTech in Computer Science from Bennett University. Today, I will be discussing a topic of theory of computation. The name of the topic is Closure Properties of Context-Free Language. Here is my introduction. In this video, I will be covering all these topics that are listed here in this slide, so you can have a look at it. Now, I will be discussing about what is context-free language. A context-free language is a language that is generated by a context-free grammar. A context-free language is accepted by a push-down automata, but such type of languages cannot be accepted by a finite automata. Why? The reason is that finite automata does not contain any memory, whereas a push-down automata contains memory. Now, I will be discussing about what is context-free grammar. A context-free grammar is a grammar that is represented by 4 tuples, and these tuples are V, T, S and P, where V stands for set of non-terminal symbols, T stands for set of terminal symbols, S stands for start symbol, and P stands for production rule. The set of non-terminal symbols are represented by using capital letters, whereas the set of terminal symbols are represented by using small letters. The production rule defined for the context-free grammar is of the form capital A implies small a, where capital A belongs to the set of non-terminal symbols and small a is equal to the set of V union T raised to the power star. That is, it can be the set of either terminal symbols, or it can be the set of non-terminal symbols, or it can be the set of both terminal as well as non-terminal symbols, or it can be an empty set. That is, it can be epsilon. Now, in order to have better understanding of context-free languages, we will now discuss an example. Let us look at the example. So the example states that for generating languages that generate equal number of A's and B's in the form of A raised to the power n, B raised to the power n. So this type of language will always produce those strings in which number of A's will be equal to number of B's, and A will always be followed by B. Please note that such type of languages cannot be accepted by a finite automata as it does not contain any memory. So the context-free grammar that is defined for such type of languages is G equals to S, A, where S, A is the set of non-terminal symbols as they are represented by capital letters. A, B is the set of terminal symbols as they are represented by small letters, and these are the production rules, where S is the start symbol. Now, let's see whether the context-free grammar is generating the language of the form A raised to the power n, B raised to the power n. So what I will do, I will start with the start symbol, and the production is S implies A, capital A, B. Now, as you can see that I can replace capital A with either A, capital A, B or epsilon. So first I will going to replace capital A with A, capital A, B. Then S will going to imply A, capital A, B, B. Okay, now what I will do, I will again replace capital A with A, capital A, B. Now S will going to imply A, capital A, B, B. Now I will going to replace this capital A with epsilon. Now S will going to imply A, B, B. Now I can write this string as A cube, B cube. So this implies that number of A's are equal to number of B's. How much ever we will going to expand, it will always going to give us the strings which will be of the form A raised to the power n, B raised to the power n, where number of A's will always be equal to number of B's and A is always followed by B. Now, I will be discussing about the closure properties of context-free language. The properties under which context-free languages are closed are union, Kleene closure, concatenation. The properties under which context-free languages are not closed are intersection and complementation. Now, we will be looking at each of these properties one by one. Now, let us understand the union property of context-free language. Now we will be discussing about the union property. Let L1 be the first context-free language. Let G1 be the corresponding context-free grammar of language L1. Let L2 be the second context-free language. Let G2 be the corresponding context-free grammar of the language L2. So, we have to prove that L1 union L2 is also a context-free language. So, let us prove this using an example. Now, consider L1 to be A raised to the power n, B raised to the power n, where n is greater than 0. So, the corresponding grammar of this language L1 is represented by G1, which is S1 implies AS1B / AB. Now, as you will expand this grammar, you will always see that the number of A's will be equal to the number of B's and A is always followed by B. Now consider language L2 to be CM D raised to the power m, where m is greater than equal to 0. So the corresponding grammar of this language L2 will be G2, which is S2 implies C S2D / epsilon. So as you will expand this grammar, you will see that it will always generate those strings in which number of C's will be equal to number of D's, and C is always followed by D. Now, the union of L1 and L2 will be represented as L, which will be equal to A raised to the power n, B raised to the power n, union C raised to the power m, D raised to the power m, where n is greater than 0 and m is greater than equal to 0 is also a context-free language, as the union says that either of the two conditions should be true. That is, either L1 should be a context-free language or L2 should be a context-free language. If this happens, then L, that is the union of L1 and L2, will also be a context-free language. So the corresponding grammar is represented by G, which is S implies S1 or S2. So in words, we can say that L1 language says that the number of A's should be equal to the number of B's, and L2 says that the number of C's should be equal to the number of D's. Therefore, their union says that either of the two conditions should be true. And if this happens, then it will also be a context-free language. So, please note that context-free languages are closed under union because there is no example that can disprove this. Now, let us understand the concatenation property of context-free language. Now, let us discuss about the concatenation property. So, let L1 be the first context-free language, let G1 be the corresponding context-free grammar of L1, let L2 be the second context-free language, and let G2 be the corresponding context-free grammar of the language L2. Now, we need to prove that L1 dot L2, or we can say L1 concatenated with L2, will also be a context-free language. So, let us consider an example. Let L1 equal to a raised to the power n, b raised to the power n, where n is greater than equal to 0. So, the corresponding grammar G1 is represented as S1 implies AS1b / epsilon. Let L2 be denoted as c raised to the power m, d raised to the power m, where m is greater than equal to 0. So the corresponding grammar, that is G2, is represented as S2 implies cs2d / epsilon. Now, if we take the concatenation of the two languages, that is L1 and L2, it will be denoted as L equals to L1 dot L2. So now after concatenation, L will be represented as a raised to the power n, b raised to the power n, dot c raised to the power m, d raised to the power m, where m is greater than equal to 0 and n is greater than equal to 0 is also a context-free language, because the concatenation of the two languages says that first, in a string, the number of A's should be equal to the number of B's, and then the number of C's should be equal to the number of D's. So if this happens, then the language is said to be context-free language. And the corresponding grammar of this language will be denoted as S implies S1 dot S2. So in words, we can say that L1 says that the number of A's should be equal to the number of B's, and L2 says that the number of C's should be equal to the number of D's. Therefore, the concatenation says that in a string that the number of A's should be equal to the number of B's, and then the number of C's should be equal to the number of D's. Then in such cases, the language will said to be a context-free language. Please note that context-free languages are closed under concatenation. Now, let us understand the Kleene closure property of context-free language. Now, let us understand the third property, which is Kleene closure. Let L1 be the first context-free language. So we have to prove that L1 star is also a context-free language. So let us consider an example. Let L1 be equal to a raised to the power n, b raised to the power n, where n is greater than equal to 0. So the corresponding grammar of the language L1 is represented as S1 implies AS1b / epsilon. Now, the Kleene closure of the language L1 is denoted as L1 raised to the power star, which is equal to a raised to the power n, b raised to the power n, where n is greater than equal to 0 raised to the power n. So this will also be a context-free language. And the corresponding grammar of L1 star will be S implies S1s / epsilon. Please note that context-free languages are closed under Kleene closure. Now, let us understand the intersection property under which context-free languages are not closed. Now, let us understand the fourth property, which is intersection. So, let L1 be the first context-free language, let L2 be the second context-free language. So we have to prove that L1 intersection L2 is also a context-free language. So, let us consider an example in order to explain the property intersection. Let L1 be equal to a raised to the power n, b raised to the power n, c raised to the power m, where n is greater than equal to 0 and m is greater than equal to 0. Let L2 be am, bn, cn, where n is greater than equal to 0 and m is greater than equal to 0. Now, the intersection of L1 and L2 will be L equals to L1 intersection L2, which is a raised to the power n, b raised to the power n, c raised to the power n, which is greater than equal to 0. And such type of languages are not context-free language. It is a context-sensitive language, and such type of languages are accepted only by the linear bounded automata. So, this is one example where context-free languages do not satisfy the intersection property and therefore they are not closed under intersection. Now, let us understand the complementation property under which context-free languages are not closed. Now, let us consider the fifth property, which is complementation. Let L1 be the first context-free language, let L2 be the second context-free language. So we have to prove that L1 complement is also a context-free language. So, let us do the proof. First, we will going to assume that the complement of every context-free language is a context-free language. We know that context-free languages are closed under union, and we assume that they are closed under complementation also. So, L1 intersection L2 is equal to L1 complement union L2 complement का whole complement, which is the De Morgan's law, right? So, we are assuming that CFL, that is context-free language, are closed under complementation. So, we say that L1 complement is a context-free language, L2 complement is also a context-free language. So, L1 complement union L2 complement will be equal to context-free language union context-free language, which will be a context-free language only. Because the union property says that either of the two conditions should be true. That is, either L1 complement should be a context-free language or L2 complement should be a context-free language. But in this case, both L1 complement and L2 complement are context-free language. Therefore, the union will also be a context-free language. Now, if I take the complement of L1 complement union L2 complement, which is represented as this, it will be equal to CFL complement. And we have already assumed that the complement of context-free language is a context-free language. Therefore, the complement of L1 complement union L2 complement will also be a context-free language. So we have proved that L1 intersection L2, which is equal to L1 complement union L2 complement का whole complement, using this De Morgan's law, is a context-free language, which is incorrect, because we have already proved in the previous case that context-free languages are not closed under intersection. Therefore, our assumption that context-free languages are closed under complementation is completely false. Therefore, context-free languages are not closed under complementation property. Thank you for watching my video. If you liked the video, please click on the like button, and if you have any query regarding this video, please put your question into the comment section and I will try to answer all of the questions as soon as possible. Thank you.